Ethane treated with O2MO2O3. Ethane treated with oxygen in the presence of molybdenum oxide. So from NCERT point of view, we know that the CH3 group will be oxidized to aldehyde. CH3 group oxidized to aldehyde. Now this aldehyde treated with dilute OH minus. Dilute OH minus. So it is a aldehyde. So we discussed already in the class, when aldehyde or ketone treated with the base like OH minus. So here first reaction is aldol, next reaction is Kenijaro, next reaction is Tollens. So we have to start from these reactions. So if these reactions are possible, don't look for the other reactions. And here first one is aldol. So in the given compound, aldol possible or not? If alpha hydrogen is present, aldol possible. If alpha hydrogen not present, aldol not possible. And Tollens reaction is aldol addition plus crossed Kenijaro reaction. Of course, here it is a alpha carbon and sp3, and it is having the two hydrogens. Therefore, this reaction is an example of aldol condensation. Since heat is given aldol condensation. Therefore, how to write aldol condensation? We will take another molecule. This is a alpha carbon and remove the H2O, and the corresponding product is CH3, CH double bond CH, CH double bond O. So it is a alpha, it is a beta, alpha beta unsaturated, alpha beta unsaturated aldehyde, alpha beta unsaturated aldehyde. The first reaction, alkene plus benzene treated with ozone and then followed by zinc H2O. So when alkene and benzene both are present, alkene undergo ozonolysis. Since here zinc is present, therefore it is a reductive ozonolysis. Reductive ozonolysis. So in place of zinc, we can also take triphenylphosphine, or we can also take dimethyl sulfide. So how to write the answer? Simply we cleave the double bond, CC double bond, and simply we should write here where the double bond is present. After breaking, we should write double bond O, double bond O. It is a reductive ozonolysis. It is treated with dilute OH minus heat. So whenever aldehyde or ketone treated with dilute OH minus, we consider first aldol condensation. If alpha hydrogen is present, Kenijaro reaction. If alpha hydrogen not present, next one is Tollens reaction, aldol addition plus crossed Kenijaro. The first we should look for these three reactions. So here CHO, it is a alpha having sp2 sp3 CH bonds, and it is also alpha sp2 sp3 CH bonds, and both alpha hydrogens are same carbons, same hydrogens. Therefore here intramolecular aldol condensation possible. Intramolecular aldol condensation. So this alpha carbon attack on this carbon, and finally we get corresponding product is So for better understanding, we can give numbering 1, 2, 3, 4, 5. Here the numbering is 1, 2, 3, 4, 5. In between 1 and 5, double bond. Here double bond. And fifth carbon connected to CHO. Fifth carbon connected to CHO. Therefore, final compound is alpha, beta. Alpha, beta, unsaturated aldehyde. Alpha, beta, unsaturated aldehyde. Alkene treated with ozone, zinc acetic acid. Alkene treated with ozone, zinc acetic acid. So we know that in the presence of zinc, ozonolysis of alkene takes place. It is called reductive ozonolysis. So simply we have to break the CC bond and just write down the double bond O, double bond O. It is called reductive ozonolysis. Now it is treated with one equivalent NaHSO3, and NaHSO3 produces electrophile SO3 minus 2, and here sulfur is nucleophile. Sulfur is nucleophile, and it is a bulky nucleophile. It is a bulky nucleophile, and we are having only one reaction in our syllabus. So according to our syllabus, sodium bisulfite react with aldehydes. Sodium bisulfite react with aldehydes and react with methyl ketones. So these kind of methyl ketones. So other ketones, they don't react because of the steric factor. So mainly we focus on the aldehydes and methyl ketones. Suppose in this question it can attack on the sulfur, can attack on the aldehyde. Sulfur also can attack on the methyl ketone. Methyl ketone. But here it is given only one equivalent of sodium bisulfite, and SO3 minus 2 is nucleophile. Therefore, here we have to compare rate of nucleophilic addition. And we know the general order rate of nucleophilic addition: HCHO greater than RCHO greater than PHCHO greater than RCOR greater than PHCOR greater than PHCOPH. So aldehydes are more reactive than ketones towards nucleophilic addition. Therefore, here we should consider with aldehyde reaction and don't bother about the ketone reaction. Ketone remains unreacted, and at aldehyde carbon, because of nucleophilic addition, it converts into SO3 minus, counter an Na plus and O minus, and that will be converted into OH. So that is, it is simply nucleophilic addition. Nucleophilic addition. Now it is ionic compound. Therefore, this type of compounds soluble in water. These type of compounds soluble in water. So this product is having an advantage. That's why aldehydes can be purified with the help of this reagent, and of course methyl ketones also. So these two compounds can be purified from impurities by using this reagent. Alkene treated with Bayer's reagent. So Bayer's reagent is cold alkaline KMnO4. Bayer's reagent is cold alkaline KMnO4. So when alkene treated with Bayer's reagent, this reaction is known as syn hydroxylation. Syn hydroxylation. Therefore, at double bond position, we should write simply OH above the plane, OH above the plane, and second molecule OH below the plane, OH below the plane. But if I rotate about this axis, both molecules are same. Both molecules are same. It is a first reaction. So when alkene treated with a Bayer's reagent, the reaction is in hydroxylation, and here finally KMnO4 converted into MnO2, and which is a brown PPT. MnO2 is brown PPT. It is treated with HiO4 or NaIO4 or lead tetraacetate. And in the presence of HiO4, it is called periodic cleavage. It is a periodic acid, therefore also called periodic cleavage. So here what happens, 1, 2 position, so 2 OH groups are present. Therefore simply what we have to do, we have to break the sigma bond. We have to break the sigma bond and write down corresponding oxidized product. So oxidized product at the double bond, at the cleavage carbons. So this is a periodic cleavage. Alkyne treated with HgSO4. It is an alkyne treated with HgSO4 and H2SO4. So this is simply electrophilic addition, because alkynes undergo electrophilic addition in the presence of electrophile Hg plus 2. So alkyne react with Hg plus 2 and give corresponding 3-membered ring, and plus R group is present, ring opening takes place. Now it react with nucleophile water. They don't mention sometimes. So water attack on the stable carbocation, and finally we get corresponding product like this. Now it is treated with H2SO4. Therefore the H plus coming from H2SO4 replaces the mercury, and finally we get corresponding enol. Double bond connected compound is known as, OH is connected known as enol. Now this enol undergo tautomerization immediately, and finally it gives corresponding ketone. And this compound name is, this group is aceto, and benzene connected to CO group. That's why it is a acetophenone. This is a acetophenone. Now this acetophenone treated with Br2OH minus. We can also take OBr minus. We can also take Br2 plus CO3 minus 2. We can also take Br minus and BrO3 minus. Br minus and BrO3 minus. So from these 4 cases, simply we can think Br2OH minus. And here ketone group is present, and especially COCH3 group is present. So immediately we should think about the haloform reaction. Since it is a bromine, we have to think about the bromoform reaction. So in bromoform reaction, what happens? We have to break the CC bond, and corresponding CO group will be oxidized to COO minus. Since it's a basic medium, I am taking COO minus, plus CH3 group converted into CHBr3. CH3 converted into CHBr3. It is a bromoform. Benzyl alcohol. It is a benzyl alcohol treated with MnO2. MnO2 is oxidizing agent. MnO2 is oxidizing agent. Especially it oxidizes allylic and benzylic alcohols. Especially it oxidizes allylic and benzylic alcohols. Since it is a benzylic carbon and OH is connected, therefore it is a benzylic alcohol and it undergo oxidation. Benzylic alcohol undergo oxidation and finally it gives corresponding product benzaldehyde. And manganese here in the +4 state and it undergo reduction into +2 state. Now the benzaldehyde treated with concentrated OH minus. So when aldehyde or ketone treated with concentrated OH minus, aldol condensation is possible if alpha hydrogen is present. Kenijaro is possible if alpha hydrogen not present. Aldol addition plus crossed Kenijaro possible. So these are the three possible reactions. And of course here it is a alpha carbon, no alpha hydrogen, and of course no sp3 carbon. That's why we think about the Kenijaro reaction. And in the Kenijaro reaction, we will take another molecule, same molecule. Suppose OH minus attacking on this carbon. So this molecule undergo oxidation. OH minus attacking molecule undergo oxidation and this molecule undergo reduction. So it is oxidation and it is reduction. So in the given reaction, same carbon undergo oxidation, same carbon undergo reduction. Therefore, it is an example of disproportionation. Rate of Kenijaro K into aldehyde to the power 2 OH minus to the power 1. Special case like very high concentration of OH minus, very high, pH almost 13 to 14. Rate is equal to K into aldehyde to the power 2 OH minus to the power 2. And rate of Kenijaro reaction directly proportional to rate of nucleophilic addition. Rate of Kenijaro reaction directly proportional to rate of nucleophilic addition. So this is about the Kenijaro reaction. The reactant has alcohol functional group. One is benzylic carbon, next carbon benzylic. One is non-benzylic alcohol treated with MnO2. And we know that MnO2 is oxidizing agent and it especially oxidizes allylic and benzylic alcohols. It especially oxidizes allylic and benzylic alcohols. Since it is a benzylic alcohol, therefore benzylic alcohol undergo oxidation and give corresponding ketone at the benzylic carbon and non-benzylic carbon not oxidized. Now it is treated with PCC, pyridinium chlorochromate. So PCC do not oxidize further ketone, but PCC oxidizes secondary alcohol to the corresponding ketone. PCC do not oxidize ketone further, but alcohol undergo oxidation. So it is our final compound. Benzene treated with CO, HCl, ZnCl2. So it is an aromatic compound. So whenever we see aromatic compound, so most of the cases we produce electrophile from the given reagents. Therefore here it is a carbon monoxide and HCl H plus. So C minus attract the proton and form corresponding product like this. Now because of resonance we can write corresponding product like this, and we know that it is electrophile. It is electrophile. Therefore aromatic compound react with electrophile. It is a electrophilic aromatic substitution. So simply what we have to do, we have to write our electrophile on the benzene. So it is our electrophile, and this reaction is known as Getterman-Koch reaction. Getterman-Koch reaction. Now it is treated with aluminum ethoxide. Aluminum ethoxide, because of vacant orbital, it is a Lewis acid. When aldehyde treated with the Lewis acid like AlOH3, so generally in the given reaction we can take any type of Lewis acid like this. So 99% we see this reagent. So when aldehyde treated with Lewis acid, this reaction is an example of Tischenko reaction. So in the Tischenko reaction, so for simplification point of view, we should oxidize one aldehyde group. We should reduce another aldehyde group, and it is a carboxylic acid. It is a alcohol. So in the presence of acidic medium, since we are doing the reaction in acidic medium, so here esterification takes place, and finally the corresponding ester is our product. Carboxylic ester is our product. So this is an example of Tischenko. So here acid plus alcohol do not form at all. Directly it converts into ester only. So only for our purpose, for our understanding purpose, I am writing acid plus alcohol. But according to the mechanism, benzaldehyde directly converts into carboxylic ester. So this functional group is carboxylic ester. You can say the compound name is benzyl benzoate. Benzyl benzoate. Benzyl benzoate. The reactant toluene treated with CrO3 and acetic anhydride. Ac2O means acetic anhydride. So this reaction is from aldehyde chapter. So the benzylic carbon in the presence of CrO3 converted into corresponding benzyl carbon connected to carboxylic ester and carboxylic ester. It is called benzylidene diacetate. Benzylidene diacetate. Now it is treated with H2O and heat. So it is a carboxylic ester. Therefore we are adding nucleophile water. Nucleophile attack, leaving group will leave. Nucleophile attack, leaving group will leave. So this is a ester hydrolysis. Ester hydrolysis. Therefore finally we get corresponding product benzene, CHOH, CH3COOH, OH and CH3COOH. And we know that when the benzene connected to two OH groups, carbon connected to two OH groups, it is called hydrate form. And hydrate form is unstable at room temperature. It immediately loses water and finally it converts into benzaldehyde. Therefore, our products are, one is benzaldehyde, one is acetic acid. Both are organic compounds. Now we are adding calcium hydroxide. That means simply OH minus. So when we add calcium hydroxide to the carboxylic acid, it is an acid and it is a base. Therefore, acid-base reaction takes place. CH3COO minus 2 times and Ca plus 2. So calcium acetate will be formed. Now the benzaldehyde and OH minus. Whenever aldehyde treated with the OH minus, aldol condensation is possible if alpha hydrogen is present. Kenizaro is possible if alpha hydrogen not present, that means sp3 alpha hydrogen. And of course another reaction, Tollens reaction, aldol addition plus aldol crossed Kenizaro. So whenever we see aldehyde ketones and base, the first we should think about these kind of reactions. And of course here it is alpha carbon but no CH bond. That's why it undergo Kenizaro. In the presence of basic medium, it undergo Kenizaro. In the Kenizaro reaction, we should consider another molecule. So OH minus attack on this carbon, and the attacked carbon undergo oxidation, and remaining aldehyde undergo reduction. So here, since it is a basic medium, COO minus and CH2OH. So this reaction is Kenizaro reaction. It is an example of disproportionation. It is an example of disproportionation reaction because same carbon oxidation and same carbon reduction. Benzoic acid treated with calcium hydroxide. Calcium hydroxide. It is an acid, it is a base. Therefore, initially acid-base reaction takes place and form corresponding calcium salt. And calcium salt, we are doing this reaction by heating. So this is called dry distillation. So in the dry distillation, what we have to do? We have to take the corresponding benzoate and Ca plus 2. While heating here, it loses CaCO3, and here this benzene will be attached to this carbon. Therefore answer pH, C double bond O, pH. This compound name is, it is a benzo and benzene connected to ketone. Therefore benzoketone, benzophenone, benzophenone. Now it is treated with HCN and NaCN. NaCN means simply Cn minus. So HCN and Cn minus. Cn minus is a strong nucleophile. And here we are having the functional group ketone. So ketone and nucleophile. We think about nucleophilic addition. Therefore, strong nucleophile attack on this carbon, pi bond shifted, and corresponding product is formed like this. Now it will take the proton from HCN and form corresponding product like this. So if the same carbon connected to OH and cyanide, this kind of functional group is known as cyanohydrin. Cyanohydrin. K equilibrium, it is a reversible reaction. So the corresponding equilibrium constant directly proportional to rate of nucleophilic addition. So for example, for K equilibrium, if they are asking for cyanohydrin, if they are asking K equilibrium for different reactants, So K equilibrium directly proportional to rate of nucleophilic addition. Benzoic acid treated with CH3Li. So this reaction is like when carboxylic acid treated with R-Li. So here initially acid base reaction takes place, RCOO minus Li plus RCOO Li. Again it reacts with R-Li, nucleophilic addition takes place and corresponding product is OLI, OLI and nucleophile R dash. Now we are adding dilute H plus. So O minus Li plus, O minus Li plus, take the proton and corresponding hydrate will form. And we know that hydrate is unstable. If the carbon connected to two OH groups, that is called hydrate form. And hydrate form is unstable. Immediately it decomposes to corresponding ketone and water. Therefore, similarly in this case also, the OH group and CH3 group. Simply answer PHCOCH3. And this compound is known as acetophenone. This compound is known as acetophenone. Now the acetophenone treated with I2 and OH minus. Acetophenone treated with I2 plus OH minus. So we can also consider I2 plus CO3 minus 2. We can also consider IO minus. We can also consider I minus plus IO3 minus. So in the presence of any one of this reagent, so first we should think about the halo form test. Since it is iodine, we should think about iodoform. So this reactant has COCH3. Therefore, it undergo cleavage at CC bond and the corresponding CO carbon will be oxidized to COO minus and CH3 will be converted into yellow dirty fellow CHI3 yellow PPT. CHI3 yellow PPT. CHI3 yellow PPT. The reactant acetyl chloride CH3 C double bond O Cl. It is called acetyl chloride. Acetyl chloride treated with Grignard reagent in the presence of CdCl2. So first here we should know about this one RMgCl plus CdCl2. These two react and it produces R2CD plus MgCl2. And when RCOCl treated with R2CD, R2CD produces nucleophile R minus, nucleophile attack, leaving group will leave. It is a nucleophilic substitution and we get our corresponding ketone. Now ketone do not react with R2CD further. So first we should recollect this reaction from our class notes. So similarly here the CH3 minus, so from this we produces first CH3 to CD. Now CH3 minus attack on this carbon, leaving group will leave. It is a nucleophilic substitution and finally we get our corresponding ketone and of course it is called acetone. It is called acetone. Now it is treated with calcium hydroxide and heat. So whenever aldehyde or ketone treated with OH minus, if alpha hydrogen is present, we should think about aldol. If alpha hydrogen not present, we should think about Kenijaro. If Tollens reaction condition is present, then we should think about aldol addition plus crossed Kenijaro. So here, since it is alpha carbon, we are having alpha sp3ch bond. Therefore, it prefers aldol condensation. So we will take another molecule of acetone, and it is alpha carbon. Remove the H2O, and the product is CH3, C double bond O, CH double bond C, methyl, methyl. So finally the product is alpha beta unsaturated ketone. Alpha beta unsaturated ketone. And this compound name is mesithyl oxide. This compound name is mesithyl oxide. Ketone treated with Br2 in acidic medium. That means we are adding H plus and electrophile Br plus. From Br2, simply we think about electrophile Br plus. So when aldehyde ketones treated with electrophile in acidic medium, so tertiary, secondary, primary in acidic medium, and it undergo electrophilic substitution. That means here it is a proton, alpha proton, it is alpha proton, and these two protons undergo tautomerization. For example, in this case, you can write the tautomer like this. And it is a enol form. Now this enol form is nucleophile because of the resonance. So this minus attack on the Br plus, and finally we get corresponding double bond OH plus and Br. Now by removal of proton, we get our corresponding product ketone, and here alkyl bromide. So this overall reaction is electrophilic substitution. Here we are adding H plus for increasing rate of formation of enol. We are adding H plus, it is a catalyst for increasing rate of formation of enol. Once enol is formed, it reacts with the electrophile. Therefore, you can write answer directly if you want. So in place of tautomeric proton, simply you can write electrophile. It is our electrophile. Now it is treated with zinc mercury conch. So whenever we see this reagent, we should think about these reactions. If CHO group is there, it will be converted to CH3. If keto group is there, converted to CH2. If NO2 group is there, converted to NH2. If NO group is there, converted to NH2. And if oxime group is there, it will be converted to corresponding amine. So these are the reactions we have to consider for zinc mercury conch. So whenever aldehyde ketone is present, here ketone is present, therefore this reaction is known as Clemmensen reduction. This reaction is known as Clemmensen reduction. Therefore the CO group will be reduced to CH2. The CO group will be reduced to CH2. Now the final product it won't react further. For example, HCl. So alkyl bromide plus HCl, this reaction is not possible. That's why it is our final compound. Because why I am thinking like this, ketone is reduced. So again, whatever the functional group is present, so that can be reduced or reacted or not, we have to check. So this is a Clemmensen reduction. The reactant is anisole, benzene connected to OCH3. It is called anisole. Anisole treated with CH3COCl and AlCl3 Lewis acid. So here we know that AlCl3 remove the Cl minus and it produces corresponding CH3CO plus. It is simply electrophile. It is a acyl electrophile. And it is an aromatic compound. So aromatic compound and electrophile, electrophilic aromatic substitution, and this reaction is known as Friedel-Crafts acylation. Friedel-Crafts acylation. And since it is a OP directing group, because of plus R, it acts as a OP directing group. Therefore, we get two products, ortho and para, and para is major. So I am writing the major product. Of course, we can also take minor product also. It is a Friedel-Crafts acylation. Now it is treated with N2H4 OH minus heat. So here two functional groups are present. One is ether, one is ketone. So N2H4 is also nucleophile. So nucleophile do not react with ether. That's why ether reduction not possible. But nucleophile can attack with the ketone. That's why this reaction possible. So from our class, we have to recollect the reaction when ketone or aldehyde treated with N2H4. Initially, we have to remove the water. Now by adding base, by heating, it loses corresponding nitrogen and forms anion, and this anion undergo neutralization and form corresponding alkane. So CO group converted to CH2. This entire reaction is known as Wolff-Kishner reduction. This entire reaction is known as Wolff-Kishner reduction. Therefore, here the keto group will be reduced to alkane. So first we should write C minus, and it undergo finally acidification, and it gives corresponding product like this. So if it undergo reduction, the corresponding product like this. Carbanion intermediate, and it finally converts into corresponding product like this. So first reaction is Friedel-Crafts acylation. Second reaction is Wolff-Kishner reduction. The reactant has alkane functional group. An alkene functional group treated with ozone and followed by zinc acetic acid. Not only zinc, we can also use triphenylphosphine. We can also use dimethyl sulfide. So this reaction is known as reductive ozonolysis. This reaction is known as reductive ozonolysis. So here what we have to do, we have to break the CC bond and write down corresponding ketone and CH2 double bond O aldehyde. Now it is treated with 1 equivalent sodium bisulfite, and here the nucleophile is S43 minus 2, sulfur is nucleophilic site. The sulfur can attack with aldehyde, sulfur can attack with ketone. That means nucleophilic addition possible. And we also know that it react with aldehydes and it react with methyl ketones, like these type of compounds, methyl ketones. So mainly these compounds react with the sodium bisulfite. So it is not methyl ketone. So because of the bulkiness, the bulky nucleophile do not react with the ketone. That's why only aldehyde react, and finally it gives corresponding CH2OH and nucleophile SO3 minus Na plus. Since it is a addition product, so addition product also called sometimes adduct. Adduct means simply addition product, and the product is water soluble. So this is an advantage for this compound. That's why we use this reaction for purification of these compounds. For purification and separation from impurities, we can use this reagent. The reactant has alkene functional group. When alkene functional group treated with ozone and H2O2, we can also use simply H2O also. This reaction is known as oxidative ozonolysis. This reaction is oxidative ozonolysis. So in oxidative ozonolysis, we have to break the alkene and we have to write corresponding ketone. In this case, we get our corresponding ketone. Of course, both ketones are same. Now the ketone treated with formaldehyde in the presence of base. So whenever aldehyde ketones treated with OH minus, if alpha hydrogen is present, aldol condensation. If alpha hydrogen not present, Cannizzaro reaction. If Tollens reaction condition present, that means aldol addition plus crossed Cannizzaro possible. Now here one reactant has alpha hydrogen, another reactant has no alpha hydrogen. So one reactant is alpha hydrogen, one reactant no alpha hydrogen, and one of the reactant is formaldehyde. So here Tollens reaction possible. So in the Tollens reaction, the alpha carbon undergo repeated aldol addition. The alpha carbon undergo repeated aldol addition. So C minus attack, CH2OH, 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 CH2OH. It is a 4 times aldol addition. Now it undergo crossed Cannizzaro. So it is aldol addition. Now it undergo crossed Cannizzaro. OH minus attack on the formaldehyde. Formaldehyde undergo oxidation because formaldehyde is more reactive than ketones towards nucleophilic addition reaction. Formaldehyde greater than RCHO greater than PHCHO greater than RCOR greater than PHCOR greater than PHCOPH. Formaldehyde is more reactive than ketones towards nucleophile. Therefore, here OH minus attack on the formaldehyde and formaldehyde undergo oxidation and the keto group will be reduced. Keto group will be reduced. So it is a crossed Cannizzaro. Aldol addition plus crossed Cannizzaro is overall reaction Tollens. The first one is oxidative ozonolysis. Second one is Tollens reaction. Epoxide treated with H2SO4. So H2SO4 means simply H plus. No nucleophile is present. Therefore, here O lone pair attract the proton. So no nucleophile is present. So after that, what we have to do? We have to cleave the CC bond and form stable carbocation. Now it undergo migration for octet stabilization. Now lone pair resonance corresponding oxonium ion formation. Now it loses proton and corresponding aldehyde. So this entire reaction is known as semi-pinacol pinacalone reaction. Not only H plus, we can also use Lewis acid like BCl3. So even though Lewis acid is given, we can take simply H plus and we can write down the answer. Now the aldehyde treated with Tollens reagent AgNO3 ammonia, otherwise AgNH32 OH. So the Tollens reagent, here mainly we should consider Ag plus and OH minus. In the presence of basic medium, we have to consider Ag plus. So what happens here? The CHO group, the aldehyde group undergo oxidation. The aldehyde group undergo oxidation by losing electrons and the silver will be reduced. Silver ion will be reduced. Suppose it is a beaker. So here silver line will form. Silver will form the line on the wall of the glass. So that's why it is called silver mirror test. Silver mirror test. Of course, it is also called Tollens test. And Tollens test is simply aldehyde is oxidized, Ag plus is reduced. Therefore, it is an example of redox reaction. It is an example of redox reaction. The reactant has two ketones. And the difference between two ketones is it is less sterically crowded ketone. It is more sterically crowded ketone. When it is treated with ethylene glycol, in the presence of acidic medium, so immediately we should recollect our reaction. When the aldehyde or ketone react with ethylene glycol in the presence of H plus, we have to remove the H2O and form corresponding cyclic acetal. And here reaction starts from nucleophilic addition. So here also nucleophilic addition. Both are nucleophilic addition. Now which one is more reactive? We know that basic rate of reaction, formaldehyde more reactive than RCHO, more reactive than PHCHO, more reactive than RCOR, more reactive than PHCOR, more reactive than PHCOPH. So here RCOR. So both are RCOR. That's why here I am considering steric factor. So here less sterically hindered ketone will react. More sterically crowded ketone will not react. That's why we have to form the cyclic acetal. We have to form the cyclic acetal with less sterically crowded ketone by losing water. Now it reacts with Grignard reagent CH3 minus MgBr plus. And we know that CH3 minus do not react with ethers, because we know very well ethers do not react with nucleophile. Without acidic medium, they don't react. So there is only one possibility left. So it is a nucleophilic addition at ketone, and corresponding product is like this. Now we are adding dilute H plus. Of course here O minus take the proton, and another one also, it is ether. So ether undergo hydrolysis in acidic medium, ether cleavage in acidic medium. So here hydrogen, here OH, here hydrogen, and here OH. Therefore the corresponding product is hydrate at this carbon and ethylene glycol tertiary alcohol. It is a product. Now we know that this hydrate form is unstable at room temperature, loses water, and finally converts into corresponding ketone. Finally converts into corresponding ketone. So it is our final product. The reactant acetone, it is a ketone. Acetone, ketone functional group, treated with base, barium hydroxide base. So whenever aldehyde or ketone treated with the base, if alpha hydrogen is present, aldol condensation. If alpha hydrogen not present, Kenny-Jarrow reaction. If Tollens reaction condition is present, then aldol addition followed by crossed Kenny-Jarrow. So first we should think about these reactions. Since it is an alpha carbon, so it is having hydrogen, we will take another ketone. Now we do aldol condensation. Because of presence of alpha hydrogen, it undergo aldol condensation. And finally we get corresponding product CH3, C double bond O, CH double bond C, CH3, CH3. So this is a alpha beta. With respect to CO, alpha beta. Alpha beta unsaturated ketone. Alpha beta unsaturated ketone. And it is also known as mesithyl oxide. It is also known as mesithyl oxide. Now it is treated with I2 and OH minus. So we can also consider OI minus. We can also consider I minus plus IO3 minus. We can also consider I2 plus CO3 minus 2. So here, because of ketone presence, this is a halo form test. And of course, in this case, iodoform test. So in the iodoform, what we have to do? We have to break this bond, and CH3 will be converted to LOPPT. It is a LOPPT, and the remaining structure CO is oxidized and alkene unaffected. Alkene unaffected. So this is our iodoform test. The reactant has two aldehydes and it is aromatic aldehyde because connected to benzene directly, and it is aliphatic aldehyde. Aliphatic aldehyde. It is treated with Fehling solution. So Fehlin has two solutions. One is Fehlin solution A, copper sulfate. Another one is Fehlin solution B, sodium potassium tartarate, also called Rockley salt, plus NaOH. So Fehlin solution A, Fehlin solution B. And we know that aromatic aldehydes, Fehlin or Benedict, no reaction. That's why Fehlin do not oxidize CHO aromatic aldehyde, but aliphatic aldehyde undergo oxidation. So aromatic aldehyde unaffected, aliphatic aldehyde oxidized to COO minus, and Fehlin solution reduced to Cu2O red PPT. It is a red PPT. Now it is treated with Tollens reagent AgNO3 plus ammonia, otherwise AgNH32OH, ammonical silver nitrate. So Tollens reagent is ammonical silver nitrate. So here mainly we should think about Ag plus and OH minus. So in the presence of basic medium, aldehyde undergo oxidation. In the presence of basic medium, aldehyde undergo oxidation. This is the oxidized part. Plus silver will be reduced to silver. Suppose it is a beaker, so it forms silver lining. This reaction is known as silver mirror test and also known as Tollens test. It is an example of redox reaction.